All right, so welcome back. Arcs and angles were the focus of our previous video lesson. Today we will begin to study arcs and chords. We'll follow a similar pattern to that of which we followed in some of the previous videos. First, we'll look at some new vocabulary, and then we'll look at some theorems that are going to help us to solve some problems. This series will include 2 videos and some class practice that you'll complete on your own and check against an answer key that I've posted to Google Classroom. So let's get started. All right, first things first, arc of chord is the minor arc formed by a chord. In circle A, chord XY cuts off 2 arcs, XY and arc XZY. XY, which is the minor arc, is the arc of chord XY. So let me highlight what I'm talking about here. So if we look, here is our chord XY that I've highlighted in yellow. That makes 2 arcs. Makes this minor arc in blue, which is XY. I'll try highlighting that again. And then it also makes another arc, which is a major arc. In that case, it is this one right here. Okay. So in this case, the arc of chord XY is going to be the chord that the arc rather that I highlighted in blue, which is this one right here. So that minor arc, arc XY, is the arc of chord, which is a segment XY. Next term, midpoint of an arc. If 2 congruent arcs have the same endpoint, then that point is the midpoint of the combined arcs. So here it reads that if arc XY is congruent to arc XZ, then X is the midpoint of, this should actually say just arc YZ, because that's still a minor arc and not a major arc. So let me show you what I mean. The first thing I'm going to do is going to show you that these 2 arcs are given to us as being congruent arcs. So, this arc XY is congruent to arc XZ. Since that's the case, this point right here, XY, that I've highlighted in purple, that is the midpoint of arc YZ. All right, so this is some new vocabulary that we're going to use. Down here, we have a theorem that applies some of that vocabulary. All right, so let's read these. It says in the same circle or in congruent circles, 1, congruent arcs have congruent chords, and 2, congruent chords have congruent arcs. So let's take a look at each of those scenarios. So if you look at the first diagram on the left, okay, that illustrates the first part of this theorem, where we've got congruent arcs, which I'm highlighting in yellow. Since those arcs are congruent, the chords that create those arcs also have to be congruent. And then if we know the opposite, if we're given the fact that we have 2 congruent chords in a circle, the arcs that are created by those chords are going to have to be congruent to each other. So let's take a look at an example problem that uses these ideas. All right, so example number 1, we're told that segment PS measures 12 units. So this segment right here, which I'm highlighting in green, measures 12 units, and segment TR measures 15 units. And what we want to do is we want to find the length of segment RQ. All right, so let's go ahead and do that. Now, the first thing that I'm noticing here is that 60 and 70 the measure of those arcs is not the same, which means that RQ cannot equal 15. The second thing that I'm looking at here is that off to the side, if I were to add these two measurements together, arc PS would equal 70 degrees. So since PS and RQ are formed, or excuse me, are congruent arcs, their chords are also congruent to each other. So that means that QR is congruent to PS, which implies that QR is equal to 12, which is the length of PS that's given to us in the beginning. Okay, so let's continue. The next theorem, a diameter that is perpendicular to a chord bisects the chord at its arc. So here we see that if AB is a diameter, then AB is perpendicular to CD, which is marked in the diagram for us. What we're also told is that AB bisects segment CD, so this chord, so these two are congruent. And it also bisects the arc, let me highlight that, bisects the arc at point B. So point B would be the midpoint of that arc. All right, so let's see how we can apply this down below. And I'm actually going to go through 3 examples of this. So here we're told that in circle A, SQ measures 12 units. AT, which is this distance right here, measures 8 units. And what we want to do is we want to find the measure of, get this, PR. That's what we're looking to find. All right, so let's see if we can do that. Okay, so based off of the theorem that we just talked about, this segment here is bisecting segment SQ. And if SQ is equal to 12, that means that SR has to equal 6. So we know that SR equals 6, and that AT equals 8. Now, these are actually a Pythagorean triple. This is a multiple of 3, 4, 5. So we can use the Pythagorean theorem here to find the length of AS. AS has to equal 10, and you can apply the Pythagorean theorem and you'll see that that's the case, or you could recognize that that's a Pythagorean triple. Now, the interesting thing about segment AS is a radius. Let me try that again. Radius of circle A. What we're trying to find is the length of PR, and PR is a diameter of circle A. So since AS is a radius and that's equal to 10, 2 times the radius should give us the length of the diameter. So PR is going to have to equal 20. Let's take a couple more examples here. Let's look at example 3. We're asked to determine the values of X and Y. Grab a pen to do that. All right, so again, we have this scenario where the diameter is intersecting the chord here. And we know that when that happens, the chord gets bisected by the diameter. So in this case, we know that, and I'm going to just grab another color pen here real quick. Let me call that M for midpoint. So since M is the midpoint, we know that X has to equal 5. Now to find the measure of, or the value of Y, what we need to know, I'm going to grab the highlighter real quick, is the measure of this arc. Okay, and the measure of that arc is actually going to be equivalent to the measure of arc EF, because this is equal to 10, this chord is equal to 10, and this chord right here is equal to 10 as well. So that would mean that arc, grab a pen here, sorry, arc AB equals 86 degrees. Now Y is half of that, because again, we're going back to the theorem where this diameter not only bisects this chord, but it also bisects the arc. So we're going to take 86 and divide that by 2. So arc BD equals 43 degrees. So X would be 5, BD would be 43. Okay, one more example. We want to find the length of a chord that is a distance 5 from the center of a circle with a radius of 8. Okay. So let me grab green. All right, so the distance from a point to a line, remember, is the length of the perpendicular segment that connects those. So there's our perpendicular segment, and we know that that's 5 units. That's given to us above. What we're also told is that the radius is equal to 8 units. So I'm going to draw in my radius from O to B, and that's going to be 8 units. And what we want to do is we want to find the length of that chord AB. So what I'm going to do is I'm actually going to find this length in blue right here, and then just double it, and we'll be able to find the length of segment AB. So I'm going to apply the Pythagorean theorem here. 5 squared, I'll just call this X for now, plus X squared equals 8 squared. That gives us 25 plus X squared equals 64. We'll subtract 64 from both sides. We're going to get X squared equals 39. And we'll take the square root of both sides, and we're going to get X equals the square root of 39. Now, I don't think 39 has any perfect square factors. So again, to find the length of AB, we're just going to have to double the value of X. So that's going to give us 2 root 39. All right, so that's going to be it for this video. I have one more video with another theorem that's really useful. Actually, just one more theorem, I think, that's really useful. I'm going to go through a few more examples, and then you guys are going to try some practice on your own. As always, if you have any questions or concerns, feel free to email me or message me through Google Classroom. I hope this video was helpful, and we will see you in the next one.